Hello, everyone. This is a recording in lieu of the recording that we were making on Wednesday's lab. Um, I lost the file for that recording, so preparing this video in in replacement of that one. I want to go over the final project and the two algorithms that you will be using. You will be creating a linear solver, a solver for a system of linear equations using two algorithms: the Gauss fulmination and LU decomposition. So I want to go over those two algorithms. I also uploaded a PDF where I clarified a little bit the um, on the format of the functions. Both functions are supposed to be solving a system of linear equations, so their inputs will be a matrix of coefficients and a vector of constants that define that system of equations, and the outputs will be a vector of variables or known x's. The solution to this linear system of equations. I also added a small equation to the PDF that will make your project a little bit clearer. You will be using both solvers to solve a regression problem, and I just added an equation that will make it a little bit more evident how to use your solvers to solve this regression problem. So that being said, I will share my screen. I will also try to do this not on the Zoom whiteboard, but on Microsoft's whiteboard, because I think the writing will be a little bit more smooth over there. Okay, so the example I want to go through is a system of equations that looks like so. We have some 6y plus 2z will be equal to 1. That's our first equation on two variables. We have 3x plus 5y plus z equal to 2. Our second equation, there's now a third variable. And our final equation, negative 8x minus y plus z will be equal to 0. So this is our system of equations, or system of three equations. We want to find a set of values for x, y, and z that will hold the three equations true simultaneously. This is not always possible. There are many problems in which there is not a single solution, but for your project, you can assume that there is actually a solution where all of the equations will be held true at the same time. Okay, so this kind of problem can be um, written as a matrix vector multiplication. We can do that by writing a matrix of coefficients 0, 6, 2, 3, 5, 1, negative 8, 1, sorry, negative 1, 1, times a vector of variables x, y, z equals a vector of constants 1, 2, and 0. All right, so if you carry out the matrix vector multiplication, you will see that 0 times x, so no term in x, plus 6 times y, plus 2 times z, 6y plus 2z equals to 1. So that is our first equation right here, 6y plus 2z equals to 1. Same for the rest of the rows. So for the first algorithm, for Gaussian elimination, we will take the matrix of coefficients and the vector of constants. So we will call this matrix here A. This vector here, we will call it X, and I will add a little arrow here to symbolize that it's a vector. So remember that here I am working on an example with 3 equations and 3 unknowns, but this can be much bigger, and your project is actually for a general case where A is n by n and X is n by 1. So n number of equations and unknowns. So this could easily be a 5 equation vector, sorry, a 5 variable vector, a 500 variable vector, 10,000 variable vector. It's an unknown size vector. So for these bigger problems, we usually stop calling them X, Y, and Z because it's becoming wieldy. Because if you have 4 variables, what will you call the next one? Maybe a W, who knows? But we will, in a more general sense, write this vector as X1, X2, and X3, and so on and so forth, right? Okay, I just wanted to clarify that, so let me erase that. And finally, this vector of coefficients, we will call it B. It is also a vector of n by 1. So in the Gaussian elimination, we have 3 valid operations. That we will apply on both A and vector B. So these 3 valid operations are swapping 2 rows, excuse me, there's something wrong with my pen. Swapping 2 rows, rows I and J. So if you go through the notes, this is defined by an operator called Tij. So if you look at the presentation, this is explained, like how to build this up. So for example, if I want to exchange rows 1 and 3 in a 3 by 3 matrix, so we start with the identity matrix 1, 1, 1. And again, this will be in a general case, like this example is for a 3 by 3, but this could be a 500 by 500 identity matrix. And we basically do the operation we want to do on the identity matrix. So if we want to swap rows 1 and 3 of our matrix A and our vector B, then we do that on the identity matrix. So if we swap rows 1 and 3, we will have 0, 0, 1 here, the third row, 0, 1, 0, the second doesn't change, and 1, 0, 0, which is the first row. And to swap rows 1 and 3 from A, let's call it A0. To take it to A1, we will be multiplying T13 times A0. All right, and same for B. T13 times A0. Excuse me, B0. Where I am calling A0 and B0 the arrays before the transformation, and A1 and B1 after the transformation. So that's the first valid operation, swapping 2 rows. The second valid operation is multiplying a row by some constant c that is not equal to 0. All right. And in the notes, this is defined as t I. So if I is the row that we're multiplying, row I, so ti of c. And it works exactly like Tij. You pre-multiply the matrix or vector you want to transform by it. And the last valid operation is adding a multiple by c that it's not 0 of a row I to a row j. And in the notes, this is called let me double check in the notes, this is called T I J of C. So here we will be multiplying a multiple of row I and adding that to row J. Okay. Okay, so having defined these three valid operations, let's go into the actual algorithm. The algorithm has two steps or stages. The first one is forward elimination. And the second one is backwards substitution. Okay, so let's go over the first one, forward elimination. So forward elimination. What we want to do here is to actually let's go back a little bit. What we want to achieve with each of these stages. First, with forward elimination, we want to have our matrix of coefficients A to be upper triangular. That means we want some stuff on the diagonal and on the upper triangular portion of the matrix. So some stuff here and zeros in the rest of the matrix. And whatever transformation we apply to A, we also apply to B. So B will still be some vector with stuff on it. And on backward substitution, so why we want to do this? Because if we have this structure, so let me write it here in the 3x3 example. If we have some value here, some value here, 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 and here, and zeros in the rest of the matrix, times x, y, z equals something, something, something. If we have this structure, then look at the bottom row. This bottom row essentially tells us that this guy by z equals this guy. So that means that we already know z. Z will just be the guy on the right divided by the guy on the left. then we could go back to the previous row. This row will tell us that this guy times y plus this time times z equals this guy. But we already know z from the previous row or from the following row. So we just multiply this guy by the value of z that we already know. We move it to the other side, and that thing divided by this guy will give us y. And we can repeat this process going up to find x. And if we had 1500 variables, we could do this 1500 times to find the 1500 unknowns. So once we have this triangular shape here, we can do the backward substitution and find all of our variables. So let's go over the proper elimination. How do we actually get to this triangular shape? So let me bring up the example that we had here. So in our example, we have 0, 6, 2, 3, 5, 1, -8, -1, 1. This is A. And we also have 1, 2, and 0. This is B. So remember that every transformation you apply to A, you also apply to B. You're doing these two things simultaneously. So how do you proceed? We do this column by column. We will start looking at the first column, this guy, and we will basically want to have something in here and zeros over here. So I explained on Monday that before doing the formal elimination on each column, we would want to do a pivoting algorithm over the row that we are concerned. So we are on the first row, we are concerned about the first column, and we do a pivoting around it. That means finding the largest absolute value in this column, in this case it's this guy, and swapping that row with the row of interest. So we will basically move this guy over here and this guy down here. So we're swapping rows 1 and 3. So that will lead us to -8, -1, 1, 3, 5, 1. The second row is unaffected, and 0, 6, 2. Same for B. 0 and 1 are exchanged, and nothing happens to the rest. All right. So again, this is something that's very easy to do for us as human beings. For a computer, for you to put this in your code, you will either want to figure out what to do with the indices or build up these transformation matrices and pre-multiply A and B with these guys. Also, when I say pre-multiply, remember that these are matrix operations, matrix multiplication. So matrix multiplication, the order actually matters. So if I have T13 times A0, it has to be in this order. This is not equal to A0 times T13. So it has to be pre-multiplied. By pre-multiplying, I mean multiplying your modifier from before, from the left. Okay, so excuse me, I don't know what happened here. There we go. So here we already made the pivoting operation. So now we will want to eliminate everything in the first column. So we are still working here, everything except this element. So let's go to the second row. So we're going in a big loop through the columns and in an inner loop through the rows. So let's go to the second row, this guy. We want to eliminate the 3, and the easiest way with the 3 basic operators that we had is adding a multiple of this guy into this second row. So which multiple? That's pretty easy. We basically want to make these 3 into a 0, so we want to find something that makes this -8 into a -3. So the easiest way to construct that is that we will have our second row 3, 5, 1 plus some multiple of -8, -1, 1, and that multiple will be something over, let me write this in green. It will be the guy we want to get rid of, 3, over the first element of the row that we are tackling, -8, and a negative sign outside. Why? Because dividing this row by its first element will make the first element 1. Multiplying by the first element of the second row will make it 3, and we want to make the 3 disappear, so we add the negative outside. Okay, so if we do this operation, we will end up with 0 here, 37 over 8 here, and 11 over 8 here. And also remember, we're doing exactly the same thing to B. So it'll be the second row, 2, so this guy, plus -3 over -8 times the first guy. In this case, it's 0, so it's irrelevant, so it's 2. All right. So our matrix and vector are now -8, -1, 1. Those didn't change. 0, 37 over 8, 11 over 8, 0, 6 over 6, 2, and the vector will be 0, 2, and 1. We are still on the first column. We already got rid of the second row. We now go to the last row. This one is already 0, but the algorithm would have been exactly the same. We would have the third row 0, 6, 2, and 1 for the vector, plus negative the guy we want to eliminate, so in this case it's a 0, so it's irrelevant, over the first guy, -8, times -8, -1, 1, and 0. But like we as humans can see that this multiplying by 0 is nonsense, so we would just get the same thing. But the computer doesn't know that, so the computer will rather go through this operation and find out this same column. Okay, so we are basically done with the first column. Let's go at the second column. So I will copy the matrix here. So we go to the second column. And again, the first thing we want to do is to pivot. Why do we want to pivot again? Because remember what we were doing before. We are dividing the guy we want to eliminate. Here it was a 0, so it doesn't matter, but whatever number it was, over the first element of the row we're concerned with. So this guy. So what happened if this guy was a 0? If this guy was a 0, then the algorithm would have blown up and it would have just have given us an error. So we want to avoid the element of the diagonal to be a 0. So here, basically, we want to avoid this guy to be a 0. And we as humans can see already that this is not a 0, but the way to preemptively eliminate any zeros for a computer wouldn't know that, so we will ask the computer to check the maximum absolute value from here downwards. So in this case, from these two elements, and move that to the diagonal. So in this case, 6 is actually bigger than 37/8. So we will want to move the third row into the second row and the second into the third one. We want to swap these two. Also, it's important, we are checking the maximum absolute value from the diagonal downwards, including the diagonal itself, because we don't want a 0 here, but nothing above it. Why? Because here we already eliminated this guy and this guy. We worked to have these guys to be 0. And if we checked, if we actually found that this guy had the maximum absolute value and we move it to the second row, then we don't have a 0 here anymore. We would have a -8, and that is exactly what we wanted to avoid. So we check it from the diagonal, including itself, downwards. Okay, so after doing the pivoting operation, we would get -8, -1, 1, 0, 0, 6, 2, 1, 0, 37/8, 11/8, 2. Okay, then we go as before. We are in the second column. We now go through the rows. There's actually only one row that we care of. It's the next row, the third one. So this guy. So we want to turn this element into 0. So to do that systematically, well, we want to do two things: turn this element into 0 and have this one remain 0. So we will not be adding the first row, because if we did, we will be having something in this position, which we don't want. So we will add something times the second row, because it already has a 0 here, and it will not affect at this 0 down here. So we will have 0, 37/8, 11/8, 2, plus some multiple of 0, 6, 2, 1. And the multiple should be the guy we want to eliminate, 37/8 over 6 and negative sign. So this will give us, let me check my notes because I don't want to make any algebra mistakes here. 1/6. And this is actually an ugly number, 47 for 59/48. So our matrix and vector are now -8, -1, 1, 0, 6, 2, 0, 0, 1/6. And this will be 0, 1, 59/48. Okay, so we are basically done. We are done with forward elimination. We have this matrix in an upper triangular form. And now we will go and do backward substitution, because as I said before, if we look at this row, at the last row, this basically tells us already what z is, because it means -1/6 times z equals 59/48. So that means that z equals 59/48 times -6, which is roughly equal, actually exactly equal to -7.375. So now we go to, to the previous row. This guy tells us 6y plus 2z, so this guy and this guy, equals 1, so this guy. But we already know z, this is already known. So we know that y will be 1, which is this guy, the element in the vector b, minus the known variables, so 2 times z, which is negative 7.375, all that divided by the coefficient of y, this guy, 1/6. So we have y to be equal to 2.625. So we go to the previous row. This guy. This guy is a full row. This guy will tell us that negative 8 times x minus y plus z equals 0. So this is a full equation. It has all of the variables, but we already know y and we already know z, so it's really easy to find out x. So x in this case will be equal to 0, the guy in the b vector, minus the summation of the known variables. So negative y plus z. So remember, these are the coefficients, negative 1 y plus 1 times z. So this is a term that in the presentation shows up as a summation, because remember, this is not only for 3 variables and 3 equations. This could be for many more. So this could be actually a really big summation. And all that divided by 1/-8, which is the coefficient of the x. And that will be equal to negative 1.25. So we're done. We have found our variables. So to recap, we have x equal to negative 1.25, y equals to 2.625, and z equals to negative 7.375. So this is the solution to our linear problem. And if we plug in these values to the original set of equations, to these equations, we will have we'll have all of them to be true at the same time. We will have expressions of the type 1 equals 1, 2 equals 2, 0 equals 0. So all of them will be held true at the same time. That's how you check that your solution makes sense. Okay, so that is the Gaussian elimination problem. To clarify, this is the backwards substitution. Okay, this is all explained in the presentation, and you can go through it slowly. Okay, so I will stop here and we will continue on the LU decomposition in a separate video, because I don't want to make this excessively long.